We discussed single particles, how to do kinetic energy and linear and angular momentum for a single particle. Today, I've got two things I want to do. Give you an 8-step approach for how to approach dynamics problems. Then we'll begin multi-particle systems. These are stepping stones on the way to rigid body dynamics, which we'll probably get to next. Let me give you this 8-step approach to dynamics problems. I think this will give a good paradigm. It's not in the book, but I think it helps clarify. So this is how to approach dynamics problems. So step 1 would be model the system to the appropriate level of detail. And that's more of an art than a science sometimes. Like, what does appropriate level of detail mean? It's kind of up to you and what the problem is. 2, you choose coordinates, and drawings are helpful. So coordinates would be the kinematic variables, like either Cartesian variables like x and y, or maybe angular variables like polar coordinates. So if we were to be think of a pendulum, the way a pendulum, we would model a pendulum for steps 1 and 2, the appropriate level of detail might be, there's just a mass at the end of a stick, and we consider the stick massless. All the mass is concentrated at a point. So that's what I mean by modeling it. Also, we would say the forces on the mass are just a force of tension and a force of gravity. So it very high level, right? And then implied in saying it's only tension and gravity is that we're not looking at air resistance. We're not going to be modeling any structural dynamics of the stick. We're not going to be doing a lot of things. And then, for example, if we were to say, okay, this is a pendulum, I'm pretty sure the dynamics is going to be mostly angular. So instead of Cartesian x and y, theta would be appropriate. So for choosing coordinates, drawings are helpful. Drawings are helpful all the way throughout. 3, we would define reference frames. And this is what we've been doing for the last several weeks, is defining and dealing with reference frames. So for example, an inertial frame, pick an inertial frame. Maybe one just pops out as the best one, but maybe not. Or other convenient frame. You definitely need an inertial frame to be able to do Newton's laws, but there might be other convenient frames for describing the location of the particle. Kinematics. So for example here, a polar coordinate system would be a useful, maybe you could call it an intermediate frame, because it's not an inertial frame. So you'll also have to have an inertial frame. In this case, maybe you would pick something that's based at the pivot point, an inertially fixed frame. And I mean, there might be more. You might have many, many frames. And then we've modeled the system, we've chosen coordinates, defined reference frames. We calculate the kinematics. So this is writing the position of the mass. So here's our mass M. The position of the mass in terms of our chosen coordinates and frame. And here it might be convenient, for example, for this particle in this pendulum example, if we're going from the pivot point to where the mass is. So where's the location of the mass with respect to the origin? That would be at R in the ER direction. So this vector R, it's the position of M with respect to O. So I could write M, R of M/O. Then you need to calculate, because we're looking forward to writing Newton's laws. Newton's laws only hold in an inertial frame. So if we've chosen an inertial frame, often an inertial frame is not going to be handed to you. It's just, here's a physical situation. How are you going to model it? You need to pick a frame. Okay, we've picked this inertial frame that's attached to the pivot. Makes sense. We're assuming here, it's again modeling of the system, we're assuming the pivot's not moving. All right, we've written the vector position. Now we need to calculate the inertial velocity and the inertial acceleration. Inertial velocity means it's the derivative of the position with respect to the chosen inertial frame. Inertial acceleration means taking the inertial derivative of the inertial velocity. So that's what's meant by these terms. Calculate inertial velocity and acceleration of that vector position. Inertial velocity means the velocity or time rate of change of position of that vector with respect to the inertial frame, okay? And then similarly, inertial acceleration means the derivative of that derivative. And this is often just abbreviated as R double dot. R is a vector double dot. Okay. Hopefully you're tracking with me. We will we'll apply this to something other than the pendulum at the end to kind of get you started on a problem. Okay, so this calculating the kinematics is what we've been focusing on for the last several weeks. And it's not like you have to do these steps necessarily in order. Like number 5 is draw a free body diagram, and maybe you do that near part 1, modeling the system. And I'm not going to give you any like particular rules. Here's how you must draw a free body diagram. I don't go that way. So for the pendulum, it would be, that force of tension, or we might just call it, the force in that rod, and then there'd be a force due to gravity. All right. Then you'd need to come up with expressions for those. Number 6 is write the dynamical equation. You might say, well, why aren't you just saying write Newton's laws? Because maybe you're not going to use F equals ma, you might use something else. So write the dynamical, or you might just say the dynamics equation. So this is, by this I mean the equations of motion, the EOM. So what would this be? Something like Newton's second law. So F, the total force, right, equals m times the acceleration. That's one way to go, right? You might instead write that rotational equation that we mentioned last time. And that's sometimes called Euler's equation. It's also been called Euler's second law, but we don't have to say anything like that. So that would be, and I realized last time I wrote M for the moment. To follow what the book writes, I'm going to start using L. So L, the total moment. So this is total moment, or total torque. Up here is total force. L equals the, I'll just write it as H dot. That's the inertial derivative of the angular momentum of the system. And that might be appropriate. For now, since we're just talking about a particle, so it's a point, doesn't have any extent, you would use one or the other, Newton's second law or Euler's equation. When we get to rigid bodies, you'll use both. But once you've written this equation of motion, now you embedded in it, you've got a second order ordinary differential equation. for your chosen coordinates. So we might write that at this point. It might require some algebra to get it in that form. You can write second order ordinary differential equations for your chosen coordinates. So if you think of the pendulum, we've done this in both ways, Newton's second law and Euler's equation for the pendulum. And we were able to write theta double dot equals negative g over the length of the pendulum, sine theta. So that's what I mean. And if you have multiple coordinates, you would have multiple second order ODEs. We might not stop there. Maybe you want to solve for the motion. So these are, so now it's just become a math or computational problem. We're done with dynamics. We're done with mechanics. It becomes a math problem. So this is the crude looking number 7. Make a nice number 7. So this would be, you solve the ordinary differential equations given initial conditions. And maybe this could be done analytically or maybe not. So for the pendulum, anytime you have a second order ODE, you've got 2 initial conditions, and we'll just say, there's time 0. The 2 initial conditions would be the initial theta dot and the initial theta. So this could be done analytically, but in very few cases. Often you just have to use a computer. So in general, let's say you're at your first job and okay, you've modeled something. Now you need to simulate this on a computer because you're not going to be able to solve it analytically. So we might say step 8, simulate on computer using whatever software package, MATLAB, Python, Julia, heard a lot of Julia. This is also, the computer is useful for, even if you got the answer analytically, visualize the results. So you could present it to your manager. And so by results, I mean the motion or whatever thing you're interested in. So simulating on a computer, and we'll later get into this. The main thing will be numerical integration. Numerical integration is the procedure by which the computer approximates the solution to an ordinary differential equation. So maybe you've heard of the Runge-Kutta algorithm, or the popular one in MATLAB is that's an ODE 45, and there's probably something analogous in Mathematica, but we'll get to that later. So hopefully these 8 steps help you along. For example, just supposing I've got this bizarre situation of a mass in a tube. So if you look at the screen, here's a tube. I don't know what this was a tube for, but it's a tube. And if I put a marble in it, it's way more effective in class because then I can swing it around. So if I put the tube in there some distance away, I don't know, it's like here, and then I rotate the tube, constant speed, constant angular velocity, I mean, maybe your intuition tells you, oh, the bead's going to get pushed out along the tube. Yeah, it is. So for this, let's say step 1 would be, what are we assuming? We're assuming we have a particle that's constrained to be along the line of the tube. You might think, but the marble, it's rolling and maybe it's going along the side. Yeah, that you ignore all that and just think of it as a particle moving along the line of the tube. Ignore the detail that it is actually a rigid body rolling and whatnot. This is where modeling becomes an art. You model to the appropriate level of detail. We've got a particle and it's moving along this tube, but the tube has some prescribed motion. We've said it's moving with some angular velocity omega. Omega is a constant. Okay, all right, that's one of the modeling assumptions. We then would think of some coordinates to describe where this marble is. It seems like the most useful thing is the distance of the marble along the tube from that rotation axis. So let's call that R. So R is our chosen coordinate. You might say, well, don't I care about some angle theta? Okay. Yeah, theta with respect to what? I don't know. I guess I'll have to pick some direction and say this is theta. Then I need to define a frame. Well, it kind of makes sense that there ought to be a frame attached to the tube. Here's my tube. I'm going to attach a frame to it. So now this is rotating around. So there's a tube frame, and I'm just giving the directions. So ER, and then a direction that's increasing, or that's in the direction of motion of the tube. Okay, E theta. And then to complete the right-handed coordinate system, EZ. That gives a third direction, ER cross E theta, EZ. EZ. So that's a frame attached to the tube. It's a rotating frame. What do I mean it's rotating? Well, it's rotating with respect to an inertial frame, but I haven't defined an inertial frame. This thing looks heavy. So maybe we can use that. So yeah, by assumption, this base isn't moving. Up here, this pivot point isn't moving. That seems like a convenient origin for an inertial frame. And you might fuss about, well, what do I make N1, N2, and N3? It's actually not going to matter. It's not. Pick something. I guess since I've defined theta this way, I'll say this is N1, this is N2. All right, and then N3, I've got N3, which is conveniently in the same direction as EZ. Cool. So now I've defined an inertial frame, a frame attached to the tube, which rotates with respect to the N frame. So I guess I can give this a name. This is the E frame attached to the tube. So I've defined the two frames, and part of the kind of embedded step for the kinematics part is you need to relate how these frames are rotating with respect to each other. In this case, the E frame, I've got the E frame attached to my tube. If I just look at the directions, those directions are rotating about the EZ direction, that third direction. And I use the right-hand rule. So my thumb's pointing in that direction and my fingers are curling in the direction that theta is increasing. So this is omega of the E frame with respect to the N frame. I'll call that theta dot. And I could say N3 or EZ. It doesn't matter. They're the same thing. But hold on. The angular rate here is omega. This is omega. Scalar omega. So omega EZ. Nice. And that's constant by assumption. And we put up here omega dot equals 0. If you look at this, kind of view it from above, viewed from above, this is the same as a polar coordinate frame. Very much a polar coordinate frame. Here's our angle theta, here's ER, here's E theta. The E frame is just a polar coordinate frame. And that's nice because then we've done some work with polar coordinate frames and getting the inertial velocity. If you want, you could look at the book example 1.2, and it goes on and on about the polar coordinate frame. I guess we haven't written the vector position yet. Let's write that vector position. So O to M, here it is, R M with respect to O is O to M, and it's just R in the ER direction. So to get the inertial velocity and inertial acceleration, right, you take the inertial, the derivative with respect to the inertial frame of this thing. Then you take the inertial derivative of that inertial derivative, right, and we'll call that R double dot. This one we'll just call R dot. You need to actually calculate what these things are. All right. And then you would plug into Newton's law, because we've got M, we've got R double dot, the acceleration. What is the total force? Well, the most notable thing is, what's the force in the ER direction? It's 0. There's no force. So by assumption, this thing is just going. We're not including some friction. So the bead, the particle, can move freely in that ER direction. There are, of course, forces keeping the bead in there, so tangential forces. If we're not even thinking of gravity, because gravity is just going to be balanced by the reaction force of the tube, or any force that's related to keeping this thing in the tube. If you want, we've got a force in the theta direction. We've got a force in the z direction, but they don't matter. They don't affect the motion in ER. So no force in the ER direction. And we've got normal reaction forces in the other two. Are those going to matter though? I don't know. So you'll have F equals total force equals mr double dot. And you could break that into its components. So consider the different components and you'll get something. So probably in the ER direction, you'll get some R double dot equation. And by here, I mean little r, the scalar r. So you'll get a second order ODE for R. And then you could apply the other steps of, once you've got your second order ODE, so that was like step 6, then you could solve that ODE given initial conditions. So try it.